Good evening, and welcome back to the Sleepy Professor. Tonight, as the world outside your window grows quiet and still, I want you to take a deep, slow breath. Let it fill your lungs completely. Now exhale. Feel your shoulders drop just a little. Settle deeper into your pillow. Adjust your blanket and let your mind begin to drift toward the very edge of everything. Because this evening's journey begins at the absolute start of time itself. Good evening, and welcome back to the Sleepy Professor. Tonight, as the world outside your window grows quiet and still, as the last sounds of the day fade into peaceful silence, I want you to take a deep, slow breath. Let it fill your lungs completely, feeling your chest expand, feeling the air flow in through your nose, cool and refreshing. Now exhale, slowly, deliberately, letting all that air flow out naturally, effortlessly. Feel your shoulders drop just a little, releasing tension you didn't even know you were holding. Settle deeper into your pillow, letting its softness cradle your head perfectly. Adjust your blanket, pulling it up to just the right spot where you feel warm and secure and comfortable. And now, let your mind begin to drift toward the very edge of everything, toward the boundary between the known and the unknown, because this evening's journey begins at the absolute start of time itself, at the very first tick of the cosmic clock. We'll be exploring the Big Bang, explained slowly and gently with patience and care. This is the calm, unhurried story of how everything you know, everything you see around you, everything you touch and feel, and everything you'll never see, no matter how powerful our telescopes become, came from a single brilliant moment of creation. It's a story that spans nearly 14 billion years of cosmic history, yet we'll take our time with it tonight. There's no rush here, no hurry, no deadlines to meet, no pressure whatsoever, just wonder, just curiosity, just the gentle unfolding of the universe's greatest story, told at a pace that invites rest rather than excitement, contemplation rather than stimulation. Before we begin our cosmic journey together, I'd love to know something personal. Where in the world are you watching from tonight? Are you under bright city lights with the gentle hum of traffic in the distance, the sounds of urban life creating a soothing white noise? Maybe you're in the countryside, where the stars shine clearer and brighter than anywhere else, where the Milky Way stretches across the sky like a river of light. Or perhaps you're somewhere in between, in a quiet suburban neighborhood where the night feels just right, balanced perfectly between silence and subtle sound. Wherever you are, whatever corner of this vast, beautiful planet you call home, it's truly a pleasure to have you here with me tonight. Your presence matters more than you know. Every view, every moment you spend here, every second of your attention helps this channel grow and reach others who seek the same peaceful blend of learning and rest, of knowledge and relaxation. And if you happen to be new to the Sleepy Professor, welcome. I mean that sincerely. From the bottom of my heart, please take just a second, just one quick moment, to like this video and subscribe to the channel. It really does help these calm explorations reach other curious dreamers like you. People who love learning, who find wonder in the universe, who appreciate the beauty of science, and who enjoy drifting off to sleep with new knowledge floating through their minds like clouds drifting across an evening sky, peaceful and serene. There's something special about falling asleep while learning, isn't there? The way facts and wonder blend together with dreams, creating something entirely unique in your unconscious mind, weaving reality and imagination into beautiful tapestries of thought. To those of you who've already joined our little constellation of subscribers, thank you. Genuinely, sincerely, thank you from the depths of my heart. You're the reason these journeys keep expanding, the reason I keep creating these videos week after week, spending hours researching and writing and recording. Your support means absolutely everything to me. It's what makes this possible, what makes this worthwhile, and if you haven't already done so, go ahead and tap that notification bell gently. That way, You won't miss the next slow drift through science and wonder. Each week brings something new, something fascinating, something carefully designed and crafted to help you relax while you learn, to soothe your mind while expanding your knowledge. Perhaps next time we'll explore black holes and their mysterious event horizons, or the fascinating nature of time itself and how it can bend and stretch, or the strange quantum realm where particles behave in ways that defy common sense and challenge everything we think we know about reality. Now, I do hope this video isn't so interesting that it actually keeps you awake tonight. That would be ironic, wouldn't it? Somewhat defeating the purpose. But if it does happen to keep you alert for a little while, well, at least you'll be lying there comfortably, peacefully, quietly learning about how the entire universe began, about the greatest mystery ever solved by human science. There are worse ways to spend a peaceful evening, certainly, and honestly, even if you drift off halfway through, even if sleep claims you before the end, your mind will continue processing these ideas in the background, weaving them into the fabric of your dreams, creating connections and understanding while you rest. So as you relax even further now, letting your muscles release their tension one by one, starting with your forehead, then your jaw, your neck, your shoulders, your arms, your hands, all the way down to your toes, let's travel back together. Not just billions of years, though we'll certainly do that. We'll traverse unimaginable spans of time, but we're going to travel back even further than that. Further than seems possible. We're going to a time before years existed at all, before the concept of time had any meaning, before centuries, before days, before hours, before minutes, before even seconds had meaning or purpose, before the concept of a calendar made any sense whatsoever, before anyone could mark the passage of time. We're going to a moment when nothing yet moved through space, when light had nowhere to shine, when darkness and brightness weren't even separate concepts yet, when the very idea of separation didn't exist. A time when a single profound question waited silently to be asked by curious minds billions of years in the future. How did something so impossibly vast, so incredibly complex, so beautifully ordered, begin from almost nothing at all? Take another slow breath now. Feel your body sinking into your mattress, becoming heavier and heavier, as though gravity itself is pulling you down into peaceful rest. Notice how your eyelids are growing heavier with each passing moment, with each word you hear. Good. That's exactly right. Perfect. We're in no hurry whatsoever. Time, after all, is what we're exploring tonight. And if time itself had a beginning, a starting point, a moment zero, then surely we can afford to take our time understanding it, can't we? We have all night, all the time in the world. The ancient mystery of origins. Before there were stars twinkling in the night sky like diamonds scattered across black velvet, before galaxies spiraled through the cosmic depths in their slow, majestic dance, before planets formed and cooled, before even time itself began to tick forward like a cosmic clock, counting out the seconds of eternity, there was mystery, pure, absolute, impenetrable mystery, the deepest mystery imaginable. For most of human history, stretching back tens of thousands of years through countless generations, through civilizations that rose and fell, through empires that conquered and crumbled, people looked up at the night sky with wonder and awe and believed it had always been there, eternal, unchanging, fixed in place like a permanent ceiling. A vast dome stretched over the world, decorated with pinpricks of light that never altered their patterns from season to season, from year to year, from century to century, from millennium to millennium. The idea that the universe actually had a beginning, a specific moment of fiery birth, a point in time before which nothing existed, would have sounded completely impossible to them. It would have seemed absurd, even laughable, perhaps even blasphemous depending on the culture and era. How could something as vast and permanent as the entire cosmos simply pop into existence? How could infinity have a starting point? Surely something so grand, so overwhelming, so utterly beyond human comprehension must have always existed, must have been there forever. That's what felt right. That's what made intuitive sense to our ancestors as they sat around their fires and gazed upward into the star-filled darkness, telling stories and pondering their place in the cosmos. In ancient times, long before science gave us tools to test our ideas, creation stories filled that enormous gap in understanding. Every culture, every civilization, every tribe, no matter how isolated, had their own explanation, their own mythology. There were gods forging the heavens with their bare hands, hammering out the stars like cosmic blacksmiths working at celestial anvils, cosmic eggs cracking open to release reality in a single moment of birth, shells falling away to reveal the universe within, endless cycles of death and rebirth spinning forever like a wheel, with no true beginning and no true end, just an eternal recurrence. World serpents coiled around the pillars of existence, primordial waters from which all things emerged, divine breath animating the void and giving life to emptiness. These were beautiful myths, rich with meaning and symbolism and deep wisdom. They told us profound truths about the human condition, about our place in the world, about morality and meaning and purpose, and our relationship with forces beyond our control. But they were all whispering the same deep intuition, weren't they? That something, somehow, started it all. That there was a beginning point, a moment of creation, even if we couldn't quite understand it, even if our limited minds couldn't fully grasp the mechanism, even if the details varied wildly from culture to culture, from continent to continent, from era to era, there was this universal sense that existence itself had an origin story, a first chapter, a moment of creation that set everything else in motion, that caused the great cosmic machinery to begin turning. The ancient Greeks, those brilliant thinkers and philosophers, debated whether the universe was finite or infinite, created or eternal, bounded or boundless. Some philosophers, like Aristotle, one of the greatest minds in history, argued for an eternal cosmos with no beginning and no end, a universe that had always existed and would always exist. Others suggested cycles of creation and destruction, worlds being born and dying in endless succession. The Hindu cosmology spoke of vast cycles spanning trillions of years, time periods so enormous, they make our lifespans seem like the blink of an eye. The Abrahamic traditions placed creation at a specific moment, ordained by divine will, God speaking the universe into existence with a word. But none of these traditions, as sophisticated as they were, as thoughtful and profound as their insights could be, could actually test their ideas against physical evidence. They were working from intuition, from philosophy, from spiritual insight, from revelation, all valuable in their own ways, all meaningful to the people who believe them, but not quite science, not quite empirical investigation. Then, slowly but surely, over centuries of careful observation and measurement, science began to listen, not to the myths, not to the stories passed down through generations, but to the light itself, the actual light from distant stars and galaxies, photons that had traveled for millions and billions of years to reach our eyes. In the early decades of the 20th century, a transformative time for astronomy, astronomers equipped with new, powerful telescopes and sensitive photographic plates that could capture faint images noticed something truly extraordinary. Something that changed everything we thought we knew about the cosmos and our place within it. Something that would revolutionize our understanding of reality itself. Distant galaxies, those faint smudges visible only through powerful telescopes, smudges that had been catalogued and studied and measured for years by dedicated astronomers, were not standing still in space like we'd always assumed. They weren't fixed in place like stars painted on a dome. They were drifting apart from each other, slowly but measurably, carried along by the stretching fabric of space itself, like boats drifting on an expanding ocean. It was as though the universe was breathing outward, expanding in all directions at once, growing larger with every passing second. Think about that for a moment. Really let it sink in deeply. Let your mind absorb the profound strangeness of it. It wasn't that the galaxies themselves were racing through the cosmos like speeding cars on a highway, burning fuel and leaving trails behind them, actively traveling through pre-existing space. No, it was something far stranger and more wonderful and more difficult to visualize. It was space itself that was expanding between them. The actual fabric of reality, the stage upon which everything performs, the canvas upon which the cosmic drama unfolds, was growing, stretching, becoming larger with each passing moment, creating new distance where there had been less distance before. And if everything was once closer together than it is now, what happens when you rewind the clock? What happens if you run the film backward, watching galaxies rush together instead of apart, watching the universe contract instead of expand? You reach a time inevitable and unavoidable when everything we see today, every single atom in your body, every photon of light streaming past Earth right now, every star and planet and grain of cosmic dust, every possibility for the future was squeezed together into a single, impossibly hot, impossibly dense state, compressed beyond imagination. Can you imagine that? Can you picture it in your mind's eye? Everything that exists, all of space and all of matter and all of energy, compressed into something unimaginably small, smaller than a galaxy with its billions of stars, smaller than a solar system with its planets orbiting peacefully, smaller than a planet like Earth, smaller than a mountain, than a grain of sand, than an atom with its nucleus and electrons, smaller perhaps than anything we can properly visualize or comprehend with our limited human minds. That incredible idea, that mind-bending concept, eventually became known, somewhat jokingly at first by a skeptical astronomer, as the Big Bang. It's a name that stuck, even though there was actually no bang at all. Not in the traditional sense we think of explosions. There was no sound, no explosion echoing through emptiness. Sound requires air to travel through, and there was no air. Just an expansion, smooth and silent and inexorable, as the universe began to unfold like a flower opening its petals toward the morning sun, like a cosmic origami unfolding to reveal its beautiful complexity. The misleading name, at the very first moment of time, or at least what we call the first moment with our limited understanding, the phrase Big Bang sounds incredibly dramatic, doesn't it? It sounds like fireworks exploding across the sky on a celebration night, bursting with light and color, like cymbals crashing in a symphony's dramatic climax, echoing through a concert hall, like a cosmic drum roll announcing the greatest show ever performed, the grandest spectacle imaginable. The name conjures images of violence, of explosive force, of spectacular pyrotechnics lighting up the darkness. But here's the thing, the crucial detail that many people miss. The name, as it turns out, is actually one of astronomy's most misleading bits of marketing. It creates entirely the wrong image in people's minds, sending them down a path of misunderstanding. The term wasn't even coined to excite the public imagination or make the theory sound more impressive to potential believers. It was actually meant as a joke, as mockery. Would you believe that? Back in 1949, during a BBC radio broadcast, a British astronomer named Fred Hoyle said it during his talk while describing a theory he didn't even believe in, a theory he actually opposed quite strongly. He was being sarcastic, dismissive even, trying to make the theory sound ridiculous. He talked about a universe that supposedly began with what he mockingly called a Big Bang, emphasizing the words to highlight how absurd he thought the concept was. He meant it as a jab, as criticism, as a way to make the theory sound absurd and unscientific to the listening public. Hoyle himself favored what was called the steady-state theory, which proposed that the universe had no beginning at all and no end either. New matter was constantly being created as space expanded, he argued, maintaining a constant average density throughout eternity. It was an elegant idea in many ways, philosophically satisfying to those who preferred an eternal cosmos, who found comfort in the idea of a universe without birth or death. But the evidence simply didn't support it. Observation after observation, measurement after measurement, pointed instead toward a universe with a definite beginning, a specific starting point in time, a moment zero. Yet the name Big Bang stuck anyway, much to the frustration of scientists ever since, and science has been patiently clarifying it ever since, trying to help people understand what really happened, what the evidence actually shows us, because names matter. Names shape how we think about things, creating mental images that can be hard to shake, and this particular name, while undeniably catchy and memorable and easy to say, fundamentally misrepresents the phenomenon it's trying to describe. It's like calling the ocean the big splash or calling gravity the big pull. Technically not wrong, but missing the deeper truth, the nuance, the real mechanism. Because here's the truth, the actual physical truth, that observations and mathematics support when we examine them carefully. The Big Bang wasn't an explosion in space like a bomb going off in an empty room, like fireworks detonating in the night sky. It was an expansion of space itself. That's a crucial distinction, perhaps the most important distinction we'll make tonight, the key to understanding everything that follows. There was no center point where it happened, no specific location in the universe where you could point your finger and say, there, that's where it all began, that's ground zero. No fireball sitting in empty darkness waiting to explode. No edges for any blast wave to reach. No shock wave traveling outward through pre-existing emptiness. Instead, everything, and I mean everything, matter, light, energy, even the very dimensions of space itself, the fundamental fabric of reality, was once closer together, much closer, unimaginably closer, and then it began to stretch outward in all directions at once, everywhere simultaneously, with no preferred direction, no center, no edge. Imagine dots drawn on the surface of a balloon with a marker. Maybe you've done this experiment in school, in a science class learning about cosmology. As you inflate the balloon, blowing air into it slowly and steadily, the dots move apart from each other in a very particular way. But they're not racing across the rubber surface like ants scurrying around frantically. They're not traveling through the rubber like bullets through paper. No, they're moving apart because the surface itself is growing underneath them. The rubber is stretching. The material between them is expanding, creating more surface area, more space between the dots. Now replace that two-dimensional rubber balloon surface with the entire three-dimensional universe, all of space as we know it, and you've got the general idea of what's happening on cosmic scales. It's space itself that's expanding. The distances between objects are increasing, not because the objects are moving through space like cars driving on a highway, but because the space between them is growing, creating more distance where there was less distance before, generating new space between existing points. If that sounds strange to you, if it makes your brain hurt a little, don't worry at all. It should sound strange. It is strange, profoundly strange. Our brains evolved to picture explosions in a very specific way, based on our everyday experiences, localized events happening in one place, like fireworks on the 4th of July, directional blasts that have a clear center and defined edges, noisy, violent events happening in one particular spot with debris flying outward in all directions. But space doesn't behave like that at all. The universe isn't expanding into something else, into some larger container or pre-existing void waiting to be filled. There's no outside for it to expand into. That question, what's outside the universe, doesn't actually make sense because outside implies space, and all of space is the universe. It's like asking what's north of the North Pole. The question contains a hidden assumption that breaks down when examined carefully. Instead, the distance between all things is simply increasing everywhere at once, uniformly on the largest scales. It's happening here, right where you're lying between you and me, right now as you listen. Though on such tiny scales we'd never notice it in everyday life. The atoms in your body aren't getting farther apart. Your cells aren't drifting away from each other. The Earth isn't drifting away from the Sun, abandoning its orbit. On those small scales, gravity and electromagnetic forces and other fundamental forces easily overcome the gentle expansion, binding things together. But on truly cosmic scales, across millions and billions of light years of distance, the effect becomes dominant and unmistakable. The primary force shaping the universe's evolution. Galaxies aren't flying through space like shrapnel from an explosion, racing away from a detonation point with explosive force propelling them. They're more like passengers on an ever-expanding fabric, like people standing on a magical carpet that's constantly growing beneath their feet, carried along for the ride without actually moving themselves. You can even see this stretching effect in the light itself, which is rather beautiful and poetic when you think about it. As space grows larger, stretching and expanding, the waves of light traveling through it get stretched too, like pulling on a spring or stretching a rubber band or accordion. This stretching turns their color gradually redder, shifting them toward the red end of the electromagnetic spectrum. Astronomers have a specific term for this phenomenon, a piece of technical jargon. They call it redshift, and it's one of the simplest, most elegant fingerprints of a growing universe, one of the clearest signatures we have. The wavelength of light literally increases as the space it travels through expands. Blue light, with its short, tight, compact wavelengths, gradually becomes green, then yellow, then orange, then red, then infrared that our eyes can't see, then microwave radiation, getting progressively longer and longer as the universe ages and grows. The light doesn't lose energy in any traditional sense, not in the way a ball rolling across a carpet might slow down. It's not wearing out or getting tired. It's simply being stretched along with everything else, pulled like taffy, extended by the expansion of space itself. So, here's a question people often ask, and it's a very natural question, one that occurs to almost everyone when they first learn about cosmic expansion. Where is the center of it all? Where exactly did the Big Bang happen? Which spot in space was the starting point? The ground zero of creation? If everything is moving away from everything else, surely there must be a central point from which everything is fleeing, right? Some special location in the cosmos that marks the epicenter of creation, the place where it all began. It's a natural question, perfectly reasonable to ask, the kind of question that shows you're thinking carefully about the implications. But here's the trick, the beautiful cosmic trick that nature plays on us. It's actually a trick question, one with no answer in the traditional sense. The answer is nowhere and everywhere, all at once, simultaneously. Let that settle in your mind for a moment, like a pebble dropped into still water, creating ripples. Every observer, no matter where they happen to be in the universe, no matter which galaxy they call home, whether they live in the Andromeda galaxy or a dwarf galaxy billions of light years away, sees other galaxies moving away from them in every direction, every single direction. North, south, east, west, up, down, and every direction in between, every angle you could possibly point. From Earth, when we look out with our telescopes scanning the night sky, examining the cosmos in all directions, it looks as though we're sitting right at the middle of all the action, at the very center of everything. Everything seems to be receding from us, drifting away. The nearby galaxies are drifting away slowly, at relatively modest speeds. The distant ones are racing away quickly, at enormous velocities. We appear to be at the very center of the cosmos, which might seem to suggest something special about our location, something unique about Earth's position in the universe. But here's the wonderful part, the truly mind-bending realization. If you were to somehow teleport yourself to a distant galaxy billions of light years away, perhaps to a planet orbiting a star in a galaxy we can barely see, you'd see exactly the same thing from there. Everything would be receding from you too, in all directions. You'd feel like you were at the center, just as much as we do here on Earth. Every point in the universe can reasonably claim to be in the middle, to be at the center of cosmic expansion. The universe doesn't have a single center point in space, no special location that marks the origin. It's more like a rising loaf of bread, dotted with raisins throughout the dough, scattered evenly. As the dough swells and rises in the oven, puffing up with heat and yeast activity, expanding in all directions, every single raisin sees all the other raisins moving away from it in all directions. The raisin on the left edge sees the others moving right. The one on the right edge sees them moving left. The one near the top sees them moving down. The one in the middle sees them moving in all directions equally, and each raisin could reasonably claim to be in the middle of the loaf, at the center of the bread. No offense to raisins, of course, but they actually make surprisingly good cosmologists when you think about it. They understand expansion intuitively, instinctively. The discovery of expansion. This brings up another important subtlety that we should address carefully and thoughtfully, because it's easy to get confused here, to mix up concepts that seem similar. When we talk about the universe, we often actually mean the observable universe, a specific limited region. That's the specific region from which light has had enough time to reach us since the very beginning, since time began ticking. You see, light has a finite speed, a speed limit built into the fabric of reality. It travels at about 300,000 kilometers every single second, which sounds incredibly fast, and it is fast, the fastest thing in existence. Nothing travels faster through space. But the cosmos also has a finite age, roughly 13.8 billion years since the Big Bang occurred. When you multiply those two numbers together and account for the expansion that's been happening all along, stretching space as the light traveled toward us across the eons, you get a visible bubble roughly 93 billion light-years across in diameter. That's our observable universe, our cosmic horizon, the boundary of what we can possibly see. But beyond that horizon, beyond that edge of visibility, beyond the limit of what our telescopes can detect, there are regions we'll never see, at least not yet. Not with current technology, not without waiting billions more years for light from those regions to finally reach us, to complete its epic journey. They aren't outside the universe, though. They're not in some other realm or dimension or parallel reality. They're simply beyond the part we can observe right now. The light from those regions hasn't had enough time to reach us yet. It's still on its way, traveling through the vastness of space at light speed, racing toward us but not yet arrived. It's like standing in a foggy valley early in the morning, just after dawn when the mist is thick and visibility is limited. You can only see to the edge of the mist, to where your vision gives out, where the fog becomes too thick to penetrate. But you absolutely know with certainty that the hills and trees continue past what your eyes allow you to see. The world doesn't end where the fog begins. There's more beyond, hidden but definitely there, existing even if invisible. The observable universe is our fog line, our horizon of visibility, the limit of what we can currently detect. The story of our expanding universe began not with a telescope gazing at something shiny and new in the night sky, not with a dramatic eureka moment where someone shouted in triumph, but with a quiet, subtle pattern hiding in starlight, waiting patiently to be discovered. It was there all along, encoded in the light from distant galaxies, waiting patiently to be noticed by someone with the right tools and the right questions to ask. In the early decades of the 20th century, when astronomy was transforming from a gentleman's hobby pursued by wealthy amateurs into a rigorous science with professional standards, astronomers were doing something quite clever and innovative. They were collecting the faint light from distant galaxies, which were still called spiral nebulae at the time, because no one quite understood what they were yet, what these fuzzy patches of light actually represented. Were they clouds within our own galaxy, the Milky Way, or were they entire galaxies themselves, island universes separated from us by unimaginable gulfs of space, entire cosmic cities of stars? They'd gather that faint light carefully, painstakingly, sometimes exposing photographic plates for hours and hours to capture enough photons to create a usable image, and pass it through prisms, splitting it into rainbows of color, creating spectra, like sunlight through a crystal, hanging in a window, creating rainbows on the wall. This technique, called spectroscopy, had already revealed the chemical composition of stars, showing that distant suns contained the same elements as Earth: hydrogen, helium, carbon, oxygen, nitrogen, iron. The universe was made of the same stuff everywhere, which was itself a profound discovery, proving a fundamental unity to creation. They expected to find variety in those rainbows, differences between galaxies, a scatter of different colors perhaps, signatures of different chemical elements burning in distant stars, glowing brightly in various wavelengths. What they found instead was something far more interesting, something that would fundamentally reshape our understanding of the cosmos and our place within it. They found consistency, but with a twist, a systematic shift. Each galaxy's spectrum contained the same familiar lines, the same chemical fingerprints they recognized from studying nearby stars in our own galaxy. But every single one of them was shifted toward the red end of the rainbow, pushed toward longer wavelengths. It was as though the light itself had been gently stretched during its long journey across space to reach Earth, like pulling on a rubber band or stretching dough. This subtle reddening, which astronomers began calling redshift with their talent for descriptive naming, was the very first hint that something enormous and profound was happening on cosmic scales, something no one had expected or predicted, something that would revolutionize our entire conception of the universe and its history. It was Edwin Hubble, working at the Mount Wilson Observatory in California, with what was then the world's largest telescope, a magnificent instrument, building carefully on the earlier mathematical work of Belgian priest and physicist Georges Lemaître, who had predicted expansion from Einstein's equations, who finally connected all the dots together. He noticed something remarkable in his data, a pattern that couldn't be mere coincidence or measurement error, something too consistent to be random. The farther away a galaxy was from us, determined through painstaking distance measurements, using various techniques, the greater its redshift seemed to be. This wasn't random scatter on a graph showing noise. This wasn't measurement error or cosmic confusion. There was a clear, undeniable pattern to it, a beautiful mathematical relationship, a beautiful linear correlation that appeared again and again in the data, no matter which galaxies he examined. The relationship eventually became known as the Hubble-Lemaître law, properly crediting both the observer who discovered it and the theorist who predicted it. It states simply, elegantly, that a galaxy's apparent speed of recession, calculated from its redshift, increases proportionally with its distance from us. The farther away it is, the faster it appears to be moving away from our vantage point. Double the distance, double the speed. Triple the distance, triple the speed. A perfect linear relationship. The first minutes. Primordial nucleosynthesis. If you could somehow rewind the entire universe to just its first few minutes of existence, before anything complex had formed, before stars ignited or planets coalesced, you'd witness the most intense, concentrated chemistry lesson imaginable, one that permanently set the stage for everything that would ever exist afterward, for all time. The cosmos back then, still glowing brilliantly, with absolutely unimaginable heat, with temperatures beyond anything we experience today, was not yet filled with stars twinkling peacefully against the darkness like jewels on black velvet. There were no galaxies spinning majestically in the void, no spiral arms stretching across space. There weren't even stable atoms yet, no complete structures with nuclei and electrons orbiting them like tiny solar systems. Instead, everything was a violent, swirling plasma of fundamental particles, a cosmic soup, protons, neutrons, electrons, and photons of light, all frantically colliding, forming and breaking apart in a furious cosmic soup that filled every corner of existence, every cubic centimeter of space. Yet somehow, in all that seemingly chaotic activity, in all that heat and violence and energy, the first atomic nuclei, the fundamental hearts of all matter, were quietly, methodically being born through nuclear fusion. This was chemistry at its most primal and essential, the most fundamental chemical reactions possible. Chemistry at the universe's very dawn, at the beginning of everything. This brief but absolutely crucial period in cosmic history is known to scientists as primordial nucleosynthesis, or Big Bang nucleosynthesis, if you prefer the more dramatic name, or if you prefer something simpler, something less technical. You can think of it as the universe's very first chemistry experiment, the grand inaugural laboratory session, the original alchemy, nature's first attempt at creating elements, and it happened between approximately 1 second and 20 minutes after the beginning, after time began. Just 20 minutes total. A blink in cosmic time, barely long enough to brew a pot of coffee or listen to a few songs on the radio, but it turned out to be one of the most productive, consequential blinks in all of history. Everything that exists in some way owes something to those first 20 minutes. Without them, the universe would be very different, radically different, perhaps impossibly different, perhaps unable to support life at all. The temperature during this period dropped from the completely unimaginable energy levels of the very first instant, when physics itself was different and our current laws break down, to something that was still staggeringly, impossibly hot by any standard we can comprehend. We're talking roughly 1 billion degrees Kelvin, a temperature that defies imagination. That's a billion, with a B, 1,000 million. 1 followed by 9 zeros, hot enough to vaporize anything instantly, to break apart any molecular bond, hot enough that the concept of solid matter is meaningless, laughable, hot enough that atoms themselves cannot exist, cannot hold together. But here's the remarkable thing, the crucial detail. At that specific temperature, in that narrow window of conditions, the universe was finally, just barely, cool enough for protons and neutrons to stick together instead of being instantly, violently blasted apart by the intense radiation and collisions happening everywhere around them. They could finally hold hands, so to speak, and stay together for more than a fraction of a second, forming the beginnings of atomic nuclei. The very first ingredient to emerge from this cosmic kitchen, this universal laboratory, was hydrogen. Simple, elegant, beautiful hydrogen, the simplest element possible, made of nothing but single protons, the simplest possible atomic nucleus, just one particle, one positively charged proton. Nothing could be simpler or more fundamental. 1 proton equals 1 hydrogen nucleus. Hydrogen would remain forever the simplest and most abundant element in the entire universe, the cosmic default. Even today, billions of years later, roughly 75% of all ordinary matter in the cosmos is still hydrogen, the same hydrogen forged in those first minutes. It's the universe's favorite element, its default setting, the baseline from which everything else is built, the foundation of cosmic chemistry. But in those first precious minutes, with all that heat and density, with particles colliding at enormous energies, something more complex could happen, something more interesting and creative. Some of those lone protons managed to meet their neutron partners in the chaotic dance of particles, in the swirling cosmic soup. When that happened, when a proton and neutron bonded together successfully through the strong nuclear force, one of nature's fundamental forces, they fused into a slightly heavier nucleus called deuterium, also known affectionately as heavy hydrogen. It's hydrogen with an extra neutron added, making it heavier and slightly more complex. Still simple, but a step up in complexity, a ladder rung higher on the cosmic ladder of element creation. Add another neutron and another proton to that deuterium, bringing the total to 2 protons and 2 neutrons bound together, and you get helium-4, the second lightest element. The very same helium that fills birthday balloons today and makes your voice squeaky and high-pitched when you breathe it in, making children laugh. The helium in the sun, fusing in its core. The helium in every star scattered across the cosmos. The helium created in those first minutes still exists, scattered throughout the cosmos, unchanged since creation. We're still using the universe's original supply, the primordial batch. A tiny fraction of the nuclear reactions went a little bit further, creating helium-3, a lighter version with 1 less neutron, slightly less stable, and an even smaller sliver of reactions managed to form lithium-7, the lightest metal on the periodic table, though calling it a metal seems almost generous given how soft and reactive it is, how easily it reacts with other substances. And that was essentially it. The complete inventory. That was the complete product list from the universe's first chemistry workshop, the cosmic kitchen's first menu. The early universe only managed to build those lightest few elements before the opportunity vanished, before the window closed. The temperatures and densities were dropping too quickly, falling too fast for anything heavier to form through fusion. The cosmic furnace was cooling down rapidly. The expansion was relentless and unstoppable, and there just wasn't enough time or energy. The window of opportunity was narrow, measured in mere minutes. After approximately 20 minutes, maybe slightly less depending on exact conditions, the cosmic forge had cooled so much that nuclear fusion simply stopped altogether, shut down completely like a fire going out. The temperature had dropped below the critical threshold needed for fusion to occur, below the point where nuclei could overcome their mutual electrical repulsion. The universe was left with a specific chemical mixture, a specific recipe that would persist essentially unchanged for billions of years afterward, frozen in place. About 75% hydrogen by mass, as I mentioned earlier, about 25% helium by mass, with helium being heavier than hydrogen, and then mere traces, tiny amounts, of deuterium, helium-3, and lithium. Those numbers might sound simple, even boring perhaps, not very impressive, but they are incredibly precise fingerprints of exactly how the early cosmos behaved, how hot it was, how dense it was. They're like a barcode stamped into the fabric of reality itself, encoding information about conditions during those first minutes, information we can still read today by measuring element abundances. It's genuinely worth pausing for a moment here to try to picture what those first minutes were actually like, to really visualize them, what it would have felt like to witness them, if such a thing were possible without being instantly vaporized by the incredible heat. The universe was expanding rapidly, space itself stretching outward in all directions, but it wasn't empty, not at all, far from it. Every single cubic centimeter of space contained billions upon billions of particles, more than you could possibly count, more than all the grains of sand on all the beaches of Earth, all still glowing brilliantly, all colliding with each other at unimaginable speeds approaching the speed of light. The temperature was so high that particles were moving at nearly the speed of light, the ultimate speed limit of the universe, 300,000 kilometers per second. Photons of electromagnetic radiation were absolutely everywhere, filling every corner of space, keeping the entire soup hot and intensely energetic, maintaining the heat through constant interaction with matter. The entire universe was glowing, radiating. Not just bright, radiant beyond anything you could imagine, beyond anything that exists today, brighter than the center of the sun, brighter than a nuclear explosion, brighter than anything we can create in laboratories. Neutrons, which are actually unstable particles when left alone by themselves outside of atomic nuclei, were gradually decaying into protons through a process involving the weak nuclear force, one of nature's four fundamental forces. A free neutron, one not safely locked inside an atomic nucleus where it's protected and stable, will spontaneously transform into a proton within about 15 minutes on average, releasing an electron and a neutrino in the process. This meant the ratio of neutrons to protons was constantly changing during this period, shifting as time passed and the universe expanded and cooled. As the universe continued expanding and cooling down, gradually becoming less dense and less hot, the conditions became less and less favorable for nuclear fusion to continue. Eventually, the temperature simply wasn't high enough anymore for nuclei to overcome their mutual electrical repulsion. Protons repel each other electrically because they're both positively charged, and at lower temperatures they don't have enough kinetic energy to get close enough for the strong nuclear force to bind them together. The window closed. The cosmic oven turned off, and the chemistry stopped, frozen in time. What remained was a universe composed primarily of hydrogen and helium, with just traces of a few other light elements. This mixture would remain essentially unchanged for hundreds of millions of years, drifting through space until gravity slowly pulled it together into the first stars. And those stars, when they ignited, would become the factories that created all the heavier elements we see today, all the carbon and oxygen and iron and gold, everything in the periodic table beyond helium. But that's a story for another section, another chapter of our cosmic tale. For now, take a deep breath. Let yourself sink even deeper into your pillow. Your eyelids are so heavy now, and know that the hydrogen atoms in the water molecules in your body, the H and H2O, were created in those first minutes of the universe. You are made of stardust, yes, but you're also made of Big Bang material. The very atoms that form you were forged in the cosmic fire at the beginning of time itself. Isn't that something worth dreaming about as you drift off to sleep? The echo of creation, cosmic microwave background. Now, let's talk about one of the most beautiful pieces of evidence we have for the Big Bang. One of the most elegant confirmations of this theory. Something so profound that when it was discovered, completely by accident, it changed everything we thought we knew about the universe's history. Take another deep breath and settle in, because this is where the story gets truly remarkable, where theory meets observation in the most satisfying way. Imagine for a moment that you're sitting by a fireplace on a cold winter evening. The fire is roaring, crackling with warmth and energy, flames dancing and leaping. The room is filled with heat, with light, with the comforting glow of burning wood. Now imagine that fire slowly dying down over the course of hours. The flames get smaller, dimmer, cooler. Eventually they fade to glowing embers, still warm but no longer blazing. Then even those embers cool, turning from bright orange to dull red to dark grey. But even after the visible glow is gone, even after the light has faded completely, the hearth still radiates warmth. You can hold your hands near it and feel the residual heat, the afterglow of the fire that once blazed so brightly. That warmth is the echo of the fire, the remnant of its former glory, proof that something hot once existed there. The universe has something similar, something absolutely extraordinary. It has an afterglow, a cosmic echo, a residual warmth left over from its fiery beginning. This is called the cosmic microwave background, or CMB for short, and it's one of the most important discoveries in the entire history of astronomy. It's the oldest light in the universe, the most ancient photons we can possibly detect, light that has been traveling through space for nearly 13.8 billion years, since the universe was just 380,000 years old. That sounds like a long time, 380,000 years. But remember, the universe is nearly 14 billion years old now. This light comes from when the universe was just a tiny infant, barely beginning its long journey through time. In the early universe, everything was incredibly hot and incredibly dense, as we've discussed. So hot that atoms couldn't exist, couldn't hold together. The electrons that normally orbit atomic nuclei were stripped away by the intense heat flying free through space. This created what physicists call a plasma, a state of matter where electrons and nuclei float separately, unbound, moving independently. This plasma had a very important property, one that would shape the entire early universe. It was opaque to light. Completely opaque, like thick fog on a winter morning, or like milk in a glass. You see, light interacts very strongly with free electrons. When a photon, a particle of light, encounters a free electron, it scatters, bouncing off in a random direction like a ball bouncing off a wall. In the dense plasma of the early universe, light couldn't travel very far at all before hitting an electron and scattering. It would travel a tiny distance, scatter, travel another tiny distance, scatter again, over and over and over. Light was trapped, imprisoned in the plasma, unable to stream freely through space. The universe was glowing brilliantly, radiating enormous amounts of energy, but that light couldn't travel. It was stuck, constantly bouncing around like a pinball in an endless machine. This meant that if you had somehow been there in the early universe, if you could have survived the incredible heat and density, you wouldn't have been able to see very far. The universe would have looked foggy, opaque, glowing uniformly in all directions, but with no visibility beyond a short distance. It would have been like being inside a glowing cloud, surrounded by brilliant light but unable to see through it to anything beyond. But then, as the universe continued to expand and cool, something magical happened, something transformative. When the temperature dropped to about 3,000 degrees Kelvin, which is still incredibly hot by our everyday standards, but much cooler than it had been, something critical occurred. At this temperature, the electrons finally had low enough energy that they could be captured by atomic nuclei, particularly by the abundant protons that formed hydrogen nuclei. The electrons settled into orbits around the protons, forming the first neutral hydrogen atoms. This process is called recombination, though that's actually a misleading name, because the electrons and protons had never been combined before. But the name stuck anyway, just like Big Bang did. This moment, this transition from plasma to neutral atoms, is sometimes called the moment of last scattering, or the surface of last scattering, and it represents a profound change in the universe's properties. Once neutral atoms formed, light could suddenly travel freely. Photons no longer scattered off electrons constantly, because the electrons were now bound inside atoms, tucked away safely. The universe became transparent, clear, like a fog suddenly lifting on a beautiful morning. Light that had been trapped, bouncing around endlessly, was suddenly released. It could stream freely through space, traveling in straight lines across the cosmos. This light has been traveling ever since, for nearly 13.8 billion years, crossing unimaginable distances, and we can still see it today. It fills the entire sky uniformly, coming from every direction equally. No matter where you point a radio telescope, you detect it. It's everywhere, all around us, bathing the Earth constantly. This is the cosmic microwave background, the afterglow of the Big Bang, the oldest light in existence. Now, you might wonder why it's called microwave background. If the universe was so hot when this light was released, glowing at 3,000 degrees, shouldn't it be visible light? Shouldn't we be able to see it with our eyes? That's an excellent question, and the answer reveals something beautiful about the expanding universe. When the light was first released 13.8 billion years ago, it was indeed visible light, glowing in shades of orange and red. But remember what we learned about expansion earlier. As space stretches, it stretches the wavelengths of light traveling through it. Over billions of years, as the universe expanded by more than 1,000 times, the wavelengths of this light stretched too, becoming longer and longer. Visible light became infrared, then far infrared, then millimeter waves, and finally microwaves. Today, this ancient light has been stretched to microwave wavelengths, to radio waves that our eyes can't see but our radio telescopes can detect. The temperature of this radiation has cooled correspondingly. Instead of 3,000 degrees, it's now just 2.725 Kelvin, which is about minus 270 degrees Celsius, just barely above absolute zero, the coldest possible temperature. It's the temperature of nearly empty space, with just a faint whisper of warmth remaining from the Big Bang. But that whisper tells us so much, reveals such profound secrets about the early universe. The discovery of the CMB is a wonderful story, full of serendipity and scientific insight. In 1964, two scientists named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in New Jersey. They were radio astronomers, studying the sky using a large horn-shaped antenna that had previously been used for satellite communications. They wanted to measure radio emissions from the Milky Way and other sources, to create maps of radio waves coming from space. But they had a problem, an annoying technical problem. No matter what they did, no matter how carefully they calibrated their instrument, they kept detecting a persistent background noise, a static that wouldn't go away. This noise was the same no matter where they pointed the antenna, whether they aimed it at the Milky Way or at empty space between galaxies, whether they observed during the day or night, winter or summer. The same hiss was there, same intensity, same frequency, same characteristics. At first, they thought it must be a problem with their equipment, some kind of interference or malfunction. They checked everything. They cleaned pigeon droppings out of the antenna, thinking maybe that was causing the problem. They tested every connection, every wire, every component, but the noise remained, stubborn and unexplained, like a puzzle refusing to be solved. Meanwhile, just a short distance away at Princeton University, a physicist named Robert Dicke had been thinking about the Big Bang theory. He realized that if the universe had truly been hot and dense in the past, there should still be remnant radiation from that era, cooled by expansion but still detectable. He predicted it should have a temperature of around 10 Kelvin and should be observable in the microwave portion of the spectrum. His team was actually in the process of building an antenna to search for this radiation when he heard about Penzias and Wilson's mysterious noise. When he learned about their discovery, he immediately understood what they had found. He turned to his colleagues and said simply, "They've got it." Penzias and Wilson had accidentally discovered the cosmic microwave background, the afterglow of the Big Bang, the oldest light in the universe. They hadn't been looking for it. They didn't even know what it was at first. But they had stumbled upon one of the most important discoveries in the history of cosmology, proof that the universe had indeed been hot and dense in the past, exactly as the Big Bang theory predicted. For this discovery, they were awarded the Nobel Prize in Physics in 1978, one of the most deserved Nobel Prizes in history. Since then, we've studied the CMB in extraordinary detail with increasingly sophisticated instruments. Satellites like COBE in 1989, WMAP in 2001, and Planck in 2009 have mapped the CMB with incredible precision, measuring not just its average temperature but also tiny variations across the sky, fluctuations of just 1 part in 100,000. These tiny variations, these subtle differences in temperature, are actually incredibly important. They represent slight density variations in the early universe, regions that were slightly more dense and regions that were slightly less dense. These density variations were the seeds from which all structure in the universe would eventually grow. The regions that were slightly denser had slightly more gravitational pull, attracting more matter. Over hundreds of millions of years, these tiny differences would grow, amplified by gravity, eventually forming the first stars, the first galaxies, and ultimately the large-scale structure we see today with galaxy clusters and superclusters. The CMB is remarkably uniform, almost perfectly smooth, which tells us the early universe was extremely homogeneous, extremely well mixed. But those tiny variations that exist tell us so much about the composition of the universe, about dark matter and dark energy, about the geometry of space itself. The CMB has become our most important tool for understanding cosmology, like a cosmic fossil preserving information from the dawn of time. And it's all around us right now, at this very moment. As you lie there listening to these words, photons from the cosmic microwave background are passing through your room, through your body, ancient light that has been traveling since the universe was just 380,000 years old. You're swimming in the afterglow of creation, bathed in the echo of the Big Bang. Every second, billions of CMB photons pass through your body, ghostly messengers from the dawn of time, carrying information about the earliest moments of cosmic history. Isn't it wonderful to think about? As your eyes grow heavier, as sleep approaches gently, know that you're connected to the very beginning of everything, surrounded by light from the universe's infancy. The CMB is physical proof, undeniable evidence that the Big Bang really happened, that the universe truly did have a beginning. It's one of the most beautiful confirmations of scientific theory in all of human history. The Dark Ages and First Light. After the cosmic microwave background was released, after the universe became transparent and light could finally stream freely through space, something interesting happened, or rather, something interesting stopped happening. The universe entered a period that astronomers call the Dark Ages, though perhaps a better name would be the Quiet Ages, or the waiting period. This wasn't darkness in the sense of evil or bad things happening. It was simply an era when the universe was dark because there were no stars yet to light it up, no galaxies shining in the void, no quasars blazing across cosmic distances. Picture the universe at this stage, roughly 380,000 years after the Big Bang. It's filled with hydrogen and helium gas, the products of those first minutes we discussed earlier, spread out uniformly in all directions. This gas is cooling as the universe continues to expand, becoming less dense, more diffuse, more spread out. The CMB light is fading, stretching to longer and longer wavelengths as space expands. There are no complex structures yet, no stars, no planets, nothing solid or bright or interesting to look at, just gas. Vast clouds of hydrogen and helium, drifting in the darkness, gradually cooling, gradually spreading out, seemingly featureless and empty. But hidden within this apparent emptiness, encoded in those tiny density variations we discussed, was the seed of everything to come. Those regions that were slightly more dense, just 1 part in 100,000 denser than average, had slightly stronger gravity, and gravity, patient and inexorable, never stops pulling. Over time, millions of years, tens of millions of years, gravity slowly drew more gas toward these denser regions. The dense areas became denser still, attracting even more matter, while the less dense regions became emptier, their material pulled away toward the growing concentrations. It was a slow process, incredibly slow by human standards, but steady and unstoppable, like water flowing downhill, always following the same inevitable path dictated by gravity. Gradually, over perhaps 100 to 200 million years after the Big Bang, the first structures began to form. Small clumps of gas, concentrated by gravity, began collapsing under their own weight. As they collapsed, they heated up, because when you compress a gas, you increase its temperature. just like a bicycle pump gets hot when you pump air into a tire. These collapsing clouds grew hotter and hotter at their centers as more and more gas fell inward, pulled by gravity, compressed by the weight of material above. Eventually, after tens of millions of years of collapse, the very first of these clouds reached a critical threshold. The temperature and pressure at the center became so extreme that nuclear fusion could begin, just like in those first minutes after the Big Bang, but now localized in these dense cores. Hydrogen nuclei, protons, began fusing together to form helium, releasing enormous amounts of energy in the process. This energy created pressure, pushing outward, balancing against gravity's inward pull, and at that moment, at that perfect balance between gravity trying to crush everything inward and fusion pushing outward with tremendous force, the first star was born, the first light ignited in the cosmos. Since the CMB faded, the Dark Ages ended. The universe lit up again, but this time with a new kind of light, stellar light, light from fusion rather than from primordial heat. These first stars were probably very different from the Sun, very different from the stars we see in our night sky today. They were likely much, much larger, perhaps 100 or even 1,000 times more massive than our Sun. The reason is simple. The universe at that time contained only hydrogen and helium, nothing heavier. Modern stars like our Sun contain small amounts of heavier elements like carbon, oxygen, nitrogen, and iron, elements that were created by earlier generations of stars. These heavier elements, even in tiny amounts, make it easier for gas clouds to cool and fragment into smaller pieces, creating smaller stars. But the first stars, forming from pure primordial gas, could only fragment into very large clumps, creating these massive stellar giants. These enormous first stars, sometimes called population 3 stars by astronomers, burned incredibly hot and bright, much brighter than our Sun, living fast and dying young. While our Sun will live for about 10 billion years total, burning its hydrogen fuel slowly and steadily, these first giants lived for only a few million years, perhaps as little as 2 million years for the very largest ones. They burned through their fuel at an incredible rate, like drag racers burning through gasoline, shining with tremendous luminosity that would have been visible across enormous distances. And when they exhausted their fuel, when the hydrogen at their cores was completely converted to helium, and then helium to heavier elements, they died in spectacular fashion. They exploded as supernovae, the most energetic explosions in the universe, releasing in a few seconds more energy than our Sun will produce in its entire 10 billion year lifetime. These explosions scattered the newly created heavy elements, carbon, oxygen, nitrogen, silicon, iron, and dozens of others, out into space, seeding the universe with the raw materials for planets, for rocky worlds, for chemistry, for life itself. Every atom in your body, heavier than hydrogen, was created inside a star and scattered by a supernova explosion. You are literally made of stardust, made of material forged in stellar furnaces billions of years ago, and scattered through space by dying stars. The first galaxies began forming shortly after the first stars appeared, perhaps 200 to 500 million years after the Big Bang. These weren't the majestic spiral galaxies we see today, like our own Milky Way with its beautiful spiral arms stretching across 100,000 light-years. The first galaxies were much smaller, irregular in shape, chaotic and disorganized. But they were bright, filled with hot young stars forming rapidly from the available gas. Over time, billions of years, these small galaxies merged together, combining through collisions to form larger and larger structures. Galaxy formation is a hierarchical process, with small things merging to form bigger things, which merge to form even bigger things, like streams combining to form rivers combining to form great rivers flowing to the sea. Our own Milky Way galaxy is the product of countless mergers over cosmic history, We can still see evidence of these ancient collisions in streams of stars orbiting our galaxy in unusual directions, remnants of smaller galaxies that merged with ours billions of years ago, and the process continues today. The Milky Way is currently in the process of absorbing several smaller dwarf galaxies, gravitationally tearing them apart and incorporating their stars into our own. And in about 4 billion years, our Milky Way will collide and merge with the Andromeda Galaxy, our nearest large galactic neighbor, creating an even larger elliptical galaxy that astronomers have already nicknamed Milkomeda. The period from about 200 million years after the Big Bang until about 1 billion years after is sometimes called the cosmic dawn, or the era of reionization. During this time, the intense ultraviolet radiation from all these young, hot stars began to ionize the hydrogen gas that still filled most of space, stripping electrons away from the hydrogen atoms and returning the universe to a partially ionized state, though much less dense than in the first moments. This ionized gas is transparent to light, unlike the opaque plasma of the very early universe, so the universe remained transparent. But it was a major transformation, changing the nature of intergalactic space. As you lie there, feeling more and more relaxed, your breathing slow and steady, your body heavy and comfortable, imagine the universe gradually coming alive with light. Imagine the first stars igniting after hundreds of millions of years of darkness, like candles being lit one by one in a vast dark cathedral. Then more stars, then small galaxies, then larger galaxies, until finally the cosmos was filled with light and structure and beauty, the universe we see today beginning to take shape. From simplicity came complexity, from uniformity came structure, from hydrogen and helium came all the elements of the periodic table, and ultimately, from those ancient stars came all of us, came life itself. The large-scale structure of the universe. Now let your breathing slow even further as we zoom out, way out, to look at the biggest picture possible, the grandest view of the cosmos. If you could somehow step outside the universe, if you could float in some impossible void beyond everything, and look back at all of creation spread before you, what would you see? What does the universe look like when viewed at the largest possible scales, when you can see billions of light years in every direction? You might expect, reasonably, that matter would be spread out randomly, uniformly, like grains of sand scattered on a beach, with galaxies sprinkled throughout space with no particular pattern or organization. After all, we've talked about how the early universe was remarkably smooth and uniform, with only tiny variations of 1 part in 100,000. But that's not what we find at all when we map the positions of millions of galaxies across vast distances. Instead, the universe has a structure, a pattern, an architecture that reveals itself only when you look at truly cosmic scales spanning hundreds of millions of light years. Galaxies are not scattered randomly throughout space, like stars thrown carelessly across the night sky. Instead, they're organized into an intricate pattern, a cosmic web of extraordinary beauty and complexity. Imagine a three-dimensional spider web stretching across the entire universe, vast beyond comprehension. Along the threads of this web, the strands and filaments, galaxies cluster together in long chains and sheets, forming structures called galaxy filaments. These filaments are the longest structures in the universe, stretching for hundreds of millions of light years, containing thousands upon thousands of galaxies, all strung together like pearls on cosmic necklaces. Where these filaments intersect, where multiple threads of the cosmic web come together, you find galaxy clusters, enormous collections of hundreds or thousands of galaxies all gravitationally bound together, orbiting around their common center of mass. These clusters are the largest gravitationally bound structures in the universe, massive beyond imagination. A typical galaxy cluster might contain 1,000 galaxies, each containing billions of stars, along with vast amounts of hot gas, filling the space between galaxies, glowing in X-rays at temperatures of millions of degrees. The total mass of a galaxy cluster can be a quadrillion times the mass of our Sun, a number so large it becomes almost meaningless, impossible to truly comprehend. And between the filaments, in the spaces where the cosmic web is empty, you find vast voids, enormous regions of space, containing very few galaxies, almost empty. These voids are typically 100 to 400 million light-years across, bubbles of near emptiness in the cosmic foam. If you lived in a galaxy inside one of these voids, your night sky would look very different from ours. Instead of seeing the glow of the Milky Way and thousands of stars and occasional fuzzy patches that are distant galaxies, you'd see mostly darkness, with only a few nearby galaxies and stars. It would be a lonely view, isolated and quiet. This cosmic web structure, this intricate pattern of filaments and clusters and voids, all emerged from those tiny density variations in the early universe, those 1 part in 100,000 fluctuations we can see in the cosmic microwave background. Over billions of years, gravity amplified these tiny differences, pulling matter together in some places and leaving other regions empty. Dense regions attracted more matter, becoming denser still, while underdense regions lost matter to their denser neighbors, becoming emptier. The process fed on itself, with the rich getting richer and the poor getting poorer, creating increasingly dramatic contrasts over time. Computer simulations of cosmic structure formation show this process beautifully. Starting from nearly uniform conditions, adding just the tiny variations observed in the CMB, and letting gravity work over billions of years, the simulations produce a cosmic web that looks remarkably similar to what we observe in the real universe. This is powerful confirmation that we understand the basic physics of how structure forms, how the universe evolved from smooth simplicity to complex structure. The cosmic web also teaches us something profound about the composition of the universe. When astronomers add up all the visible matter they can detect, all the stars in all the galaxies, all the gas between galaxies, everything that emits or absorbs light, they find it accounts for only about 5% of the total mass energy of the universe. Just 5%. That's all the ordinary matter. Everything made of protons and neutrons and electrons, everything on the periodic table, every atom in your body, every star and planet and gas cloud, all of it, everywhere in the universe, is just 5% of the total. So where's the rest? What makes up the other 95%? This is where things get truly mysterious, truly strange, as we enter the realm of dark matter and dark energy, two of the greatest mysteries in all of modern physics. The mystery of dark matter. About 27% of the universe consists of something called dark matter, and I must tell you honestly, we don't really know what it is, not precisely. We know it's there because we can see its gravitational effects, but we can't see the matter itself. It doesn't emit light, doesn't absorb light, doesn't reflect light, it doesn't interact with electromagnetic radiation at all, which is why we call it dark. It's invisible, undetectable by telescopes no matter what wavelength we observe at, whether visible light, infrared, radio waves, X-rays, or gamma rays. Dark matter is completely transparent to all forms of light. How do we know it exists if we can't see it? Through gravity, that patient and inexorable force we've discussed. Gravity affects everything with mass, and dark matter has mass. Lots of it. In fact, there's about 5 times as much dark matter as ordinary matter in the universe. It completely dominates the mass budget of the cosmos. The first hints of dark matter came in the 1930s, when astronomer Fritz Zwicky studied the motion of galaxies in the Coma cluster, a large cluster of galaxies about 300 million light-years from Earth. He measured how fast the galaxies were moving, orbiting around the cluster's center. When he calculated how much mass would be needed to keep these galaxies gravitationally bound, preventing them from flying apart into space, he found something shocking. The visible galaxies, all the stars he could see, provided only about 1% of the mass required. There had to be enormous amounts of invisible matter providing the additional gravity, holding the cluster together. He called this missing matter dark matter, and the name stuck, though for decades, most astronomers dismissed his findings as probably due to measurement errors. But evidence continued to accumulate over the following decades. In the 1970s, astronomer Vera Rubin made careful studies of how stars orbit within galaxies, measuring their velocities at different distances from the galactic center. According to Newton's laws of gravity, which work perfectly well for describing planetary orbits in our solar system, stars farther from the center of a galaxy should orbit more slowly, just as outer planets in our solar system orbit the Sun more slowly than inner planets. Mercury races around the Sun in just 88 days, while distant Neptune takes 165 years. But that's not what Rubin found. Instead, stars at the outer edges of galaxies move just as fast as stars closer to the center, sometimes even faster. The rotation curves stay flat instead of declining as expected. This was completely unexpected, completely contrary to what Newton's laws predicted based on the visible matter alone. The only explanation is that galaxies are embedded in enormous halos of dark matter, extending far beyond the visible stars, providing additional gravity that affects the orbital velocities. These dark matter halos are much larger than the visible galaxy, perhaps 10 times larger, like a huge invisible sphere surrounding the bright disk of stars we can see. Since then, many other lines of evidence have confirmed dark matter's existence. Gravitational lensing, the bending of light by massive objects predicted by Einstein's general relativity, shows that galaxy clusters contain far more mass than their visible matter can account for. The pattern of fluctuations in the cosmic microwave background can only be explained if dark matter exists, and outweighs ordinary matter by a factor of 5. The cosmic web structure we discussed earlier requires dark matter to form. Without it, gravity wouldn't have been strong enough to pull matter together into the structures we observe. So we're confident dark matter exists, that it's real, but we still don't know what it's made of, what particles comprise it. It's not any form of ordinary matter made of protons, neutrons, and electrons. We've ruled that out through various observations. It must be some exotic particle that interacts only through gravity, not through electromagnetism or the strong nuclear force. Physicists have proposed various candidates with intriguing names: WIMPs, weakly interacting massive particles, axions, sterile neutrinos, and others. Experiments deep underground and on satellites are searching for these particles, trying to detect them directly or create them in particle accelerators. But so far, despite decades of searching, we haven't directly detected dark matter particles. It remains one of the great unsolved mysteries in physics, a cosmic puzzle waiting to be solved. As you lie there, feeling your body growing heavier, sinking deeper into your mattress, consider this: you're swimming through dark matter right now. The Earth is moving through the Milky Way's dark matter halo, and dark matter particles are passing through your body constantly, billions of them every second. But they interact so weakly that they pass right through you, through the Earth, through everything, like ghosts. You never notice them. They leave no trace. Yet without dark matter, galaxies wouldn't exist, stars wouldn't have formed, planets wouldn't exist, and you wouldn't be here listening to this. Dark matter is essential to cosmic structure, to the universe as we know it, even though we can't see it or touch it or detect it directly. Dark energy and the accelerating universe. And now we come to the biggest mystery of all, the most profound puzzle facing modern cosmology. Something even stranger than dark matter. Something that makes up an astonishing 68% of the universe, dominating everything else. This is dark energy, and I must confess, We understand it even less than we understand dark matter. Dark energy is perhaps the deepest mystery in all of science, a phenomenon so strange and unexpected that when it was first discovered, many scientists simply couldn't believe it. Some thought it must be a mistake, an error in the observations or calculations. For most of the 20th century, after Hubble discovered that the universe is expanding, astronomers debated what would ultimately happen to this expansion. Would it continue forever, with galaxies flying apart eternally? Or would gravity eventually slow the expansion down, perhaps even reversing it, causing the universe to collapse back on itself in a big crunch, the opposite of the Big Bang? The answer depended on how much matter the universe contained. If there was enough matter, enough mass creating enough gravitational attraction, gravity would eventually overcome the expansion and pull everything back together. If there wasn't enough matter, the universe would expand forever, though gradually slowing down over time as gravity worked to break the expansion. Everyone assumed the expansion must be slowing down. That seemed obvious, inevitable. Gravity attracts, pulling things together, so it must be working to slow the expansion, even if it wasn't strong enough to reverse it entirely. The question was only whether the slowdown was fast or slow, whether the universe would eventually recollapse or expand forever at a decreasing rate. In the 1990s, two teams of astronomers set out to measure how much the expansion was slowing down by observing very distant supernovae. They used a special type of supernova called Type Ia, which occurs when a white dwarf star accumulates too much mass from a companion star and explodes. These supernovae are remarkably consistent in their brightness, always reaching about the same peak luminosity, which makes them excellent standard candles for measuring cosmic distances. By measuring how bright they appear from Earth and comparing that to their known intrinsic brightness, astronomers can calculate how far away they are, and by measuring their redshift, they can determine how fast the universe was expanding when the light was emitted. Both teams, working independently, spent years carefully measuring dozens of distant supernovae, billions of light-years away, and when they analyzed their data, both teams found the same shocking, completely unexpected result. The expansion of the universe isn't slowing down at all. It's speeding up, accelerating. The universe is expanding faster now than it was billions of years ago, and the expansion rate is increasing over time. This was so surprising, so contrary to every expectation, that both teams initially thought they'd made a mistake. They checked and rechecked their data, their calculations, looking for errors. But the result held up. The universe really is accelerating. This discovery, announced in 1998, revolutionized cosmology and earned the three team leaders the Nobel Prize in Physics in 2011. But it raised an enormous question: what's causing this acceleration? Gravity should be slowing things down, not speeding them up. Something must be working against gravity, pushing space to expand faster and faster. Physicists call this mysterious something dark energy, though that's really just a placeholder name for our ignorance, a label for something we don't understand. Dark energy appears to be a property of space itself, an intrinsic energy that space possesses. As the universe expands and more space comes into existence, there's more dark energy, which accelerates the expansion further, creating even more space, and so on in a feedback loop. Dark energy doesn't dilute as the universe expands, unlike matter which becomes less dense as space grows. Instead, dark energy maintains a constant density, meaning the total amount increases as the volume of space increases. The simplest explanation for dark energy is something called the cosmological constant, represented by the Greek letter lambda. This is actually the same constant that Einstein added to his equations back in 1915 to try to force the universe to be static, before Hubble discovered expansion. Einstein later called this his biggest blunder, removing the cosmological constant from his equations. But it turns out he may have been right all along. just for the wrong reasons. A cosmological constant represents energy inherent in the vacuum of space itself, energy that space possesses simply by existing. In quantum field theory, the quantum physics theory that describes fundamental particles and forces, empty space isn't truly empty. It's filled with virtual particles constantly popping in and out of existence, quantum fluctuations happening at incredibly tiny scales. These fluctuations should contribute energy to the vacuum, and this vacuum energy could be the source of dark energy. However, there's a huge problem, perhaps the biggest problem in all of theoretical physics. When physicists calculate how much vacuum energy quantum field theory predicts, they get a number that's about 10 circumflex 120 times larger than the observed dark energy density. That's 1 followed by 120 zeros, an incomprehensibly large discrepancy. It's the worst prediction in the history of physics, off by more factors of 10 than there are atoms in the observable universe. Clearly something is very wrong with our understanding, but we don't know what. This is called the cosmological constant problem, and solving it remains one of the greatest challenges in theoretical physics. So dark energy remains deeply mysterious, its nature unknown, its origin unexplained. We can measure its effects, observe how it accelerates the expansion, but we can't explain why it exists or why it has the precise value we observe. It's a humbling reminder that despite all our scientific progress, despite all we've learned about the universe, there's still so much we don't understand. What will happen to the universe in the far future if dark energy continues to dominate? The expansion will accelerate faster and faster, pushing galaxies farther and farther apart at ever-increasing rates. Eventually, distant galaxies will recede from us faster than light can travel through the expanding space between us, disappearing beyond our cosmic horizon forever. In trillions of years, observers in our galaxy will look out and see only darkness, with all external galaxies having vanished from view. Eventually, even galaxies themselves may be torn apart as dark energy grows stronger, and in the unimaginably distant future, perhaps dark energy will tear apart solar systems, planets, atoms themselves, ripping the fabric of space apart in what physicists call the Big Rip. But that's trillions upon trillions of years in the future, so distant it's almost meaningless. For now, we simply observe, measure, and wonder. As you drift closer to sleep now, your breath slow and rhythmic, your body completely relaxed, rest assured that these mysteries, while profound, don't diminish the beauty of what we've learned. We've traced the universe's history from the first fraction of a second to the present day. We've watched stars and galaxies form, elements created, structure emerge from simplicity. And we're here, you and I, conscious beings capable of understanding our cosmic origins, of contemplating the universe's grandest mysteries. We are the universe reflecting on itself, stardust pondering stardust. Our place in the cosmic story. Now, as you lie there in the darkness, your breathing slow and steady, your mind drifting peacefully between waking and sleeping, let's bring this vast cosmic story back to something more personal, more immediate, more intimate. Let's talk about us, about Earth, about you and me, and how we fit into this 3.8 billion year epic we've been exploring together. Every atom in your body has a story stretching back to the beginning of time. The hydrogen atoms that make up most of the water in your cells, the H and H2O, those specific hydrogen nuclei, those single protons, were created in the first minutes after the Big Bang when the universe was less than 20 minutes old. They've been traveling through space for 13.8 billion years, cycling through countless stars and planets and clouds and oceans, and now they're part of you, temporarily, for the brief span of your lifetime. You are made of the universe's original material, primordial matter from the cosmic dawn. The carbon atoms that form the backbone of every molecule in your body, The oxygen you breathe with every slow, peaceful breath you're taking right now, the nitrogen in your DNA, the calcium in your bones, the iron in your blood that carries oxygen through your veins, all of these heavier elements were created inside stars that lived and died billions of years ago. Those ancient stars, massive giants far larger than our sun, fused lighter elements into heavier ones through nuclear fusion reactions in their cores, building up the periodic table element by element. When those stars exhausted their fuel, they exploded as supernovae, scattering their enriched material across space in spectacular cosmic fireworks displays. That material drifted through interstellar space, mixed with gas and dust, and eventually collapsed under gravity to form new stars, including our Sun, along with its family of planets, including Earth. Our Sun and the entire solar system formed about 4.6 billion years ago from a rotating cloud of gas and dust called the solar nebula. This cloud was enriched with heavy elements from previous generations of stars, containing all the ingredients necessary for rocky planets, and eventually for life itself. Gravity pulled most of the material toward the center, forming the Sun, while the remaining material flattened into a disk that gradually coalesced into planets, moons, asteroids, and comets. Earth formed from countless collisions between smaller rocky bodies, growing larger over millions of years through violent impacts that released enormous amounts of heat, melting the entire planet into a molten ball of rock and metal. Gradually, over tens of millions of years, the young Earth cooled, developing a solid crust floating on a still molten interior. Water vapor in the atmosphere condensed and fell as rain, perhaps raining for thousands of years continuously, filling the ocean basins. The early Earth was a harsh, inhospitable place, with no oxygen in the atmosphere, constant volcanic activity, and probably frequent impacts from asteroids and comets, still littering the young solar system. But somehow, in that hostile environment, something miraculous happened. Life began, probably in the oceans, perhaps near hydrothermal vents on the ocean floor, or in shallow tide pools, or some other protected environment. The exact mechanism remains one of science's great mysteries, but somehow, simple organic molecules organized themselves into self-replicating systems. Life emerged, fragile and simple at first, but possessing the remarkable ability to reproduce, to make copies of itself. This happened surprisingly quickly in cosmic terms, perhaps within a few 100 million years after Earth's formation, showing that the transition from chemistry to biology might be easier than we once thought. Once life began, evolution through natural selection took over, slowly but steadily increasing complexity over billions of years. For most of Earth's history, life remained microscopic, single-celled organisms too small to see with the naked eye. But those simple cells gradually evolved more sophisticated capabilities. Some learned to harvest energy from sunlight through photosynthesis, producing oxygen as a waste product. Over hundreds of millions of years, this oxygen accumulated in the atmosphere, completely transforming Earth's environment and making possible new forms of more complex life that use oxygen for energy. About 600 million years ago, life exploded in diversity during the Cambrian period, developing the major body plans we see today. Life moved from the oceans onto land, colonizing every available environment. Plants spread across the continents, creating forests and grasslands. Animals evolved incredible diversity, from insects to dinosaurs to mammals. And then, quite recently in cosmic terms, just a few million years ago, a particular branch of primates in Africa began developing larger brains, more sophisticated tools, language, and abstract thought. Humans emerged unique in our ability to contemplate the universe, to ask questions about our origins, to do science and philosophy and art. You are the product of this entire cosmic journey, all 13.8 billion years of it. You are a way for the universe to know itself, to understand its own history, to contemplate its own vastness. The atoms in your body were forged in the nuclear furnaces of ancient stars. The water you drink was delivered to Earth by comets from the outer solar system. The oxygen you breathe was produced by countless generations of photosynthetic organisms over billions of years. You are deeply connected to everything, to the stars above, to the planet beneath you, to all life around you. You are not separate from the universe. You are the universe, a small but significant part of it, looking at itself with wonder and curiosity. And here's something truly remarkable to contemplate as you drift towards sleep. We are living in a very special time in cosmic history. We exist during an era when stars still shine brightly, when galaxies are still visible in our telescopes, when the cosmic microwave background can still be detected. Trillions of years from now, intelligent beings, if they exist, will look out at a very different universe. Dark energy will have accelerated the expansion so much that all galaxies beyond our local group will have disappeared beyond the cosmic horizon, receding faster than light can travel through expanding space. The CMB will have redshifted to such long wavelengths, it will be undetectable. Future astronomers will see only their own galaxy in an otherwise empty dark sky. They won't be able to see the evidence of the Big Bang that we can see. They might not be able to figure out that the universe had a beginning, or that it's expanding. They'll be cosmologically isolated, cut off from the larger universe by expansion. But we live now, at this moment in cosmic history, when the evidence of our origins is still visible, still accessible. We can look back almost to the beginning of time. We can see galaxies as they were billions of years ago. We can detect the afterglow of creation itself. We are privileged observers, living at a time when the universe reveals its secrets to those who look carefully enough, who ask the right questions, who build the right instruments. The ongoing journey. As you sink deeper into relaxation, your eyelids so heavy now they can barely stay open, your breathing deep and regular, let's reflect on how far we've come tonight in our gentle exploration. We started at the very beginning of everything, at the moment when time itself began, when the universe emerged from an impossibly hot, impossibly dense state. We watched as space expanded and cooled, as the first atomic nuclei formed in those crucial first 20 minutes. We witnessed the release of the cosmic microwave background when the universe became transparent, ancient light that still bathes us today. We watched the Dark Ages give way to the cosmic dawn as the first stars ignited, lighting up the universe after hundreds of millions of years of darkness. We saw those massive first stars live and die, creating and scattering the heavy elements necessary for planets and life. We observed how gravity shaped matter into the cosmic web, with its vast filaments of galaxies surrounding enormous voids. We contemplated the mysteries of dark matter and dark energy, those invisible components that dominate the universe's mass and energy budget, yet remain frustratingly undetected and unexplained. And we brought the story home, connecting those vast cosmic processes to you personally, showing how you are made of stardust, how your atoms have been recycling through the cosmos for billions of years, how you are an intimate part of this grand cosmic story, rather than a separate observer watching from outside. This is what makes cosmology, the study of the universe as a whole, so profoundly meaningful and deeply moving. It's not just abstract physics and distant galaxies with no connection to our lives. It's our origin story, our family history written in starlight and radiation, and the motion of galaxies. It tells us where we came from, what we're made of, and how we came to exist. It connects us to the deepest past and the farthest reaches of space. It reveals that we are not alone or isolated or separate, but intimately woven into the fabric of existence itself. Science is humanity's greatest achievement in many ways, our most successful method for understanding reality, for separating truth from wishful thinking or inherited assumptions. Through careful observation, rigorous measurement, mathematical modeling, and the willingness to change our minds when evidence demands it, We've figured out the universe's history and structure with remarkable precision. We know the universe's age to within about 1% accuracy. We've mapped the distribution of galaxies across billions of light years. We've detected gravitational waves from colliding black holes, confirming predictions Einstein made a century ago. We've taken pictures of black hole shadows, photographed light from the first billion years after the Big Bang, and detected planets orbiting other stars. And yet, for all we've learned, so much remains mysterious, unknown, waiting to be discovered. We don't know what dark matter is made of, despite decades of searching and despite knowing it must exist. We have no idea why dark energy exists or why it has the value it does. We don't understand what happened in the very first fraction of a second after the Big Bang, when quantum effects were important on cosmic scales. We don't know if our universe is the only one, or if countless other universes exist beyond our cosmic horizon. We don't know if life exists elsewhere in the cosmos. Though the universe is so vast it seems unlikely we're alone. We don't know why the laws of physics have the particular forms they do, or whether they could have been different. These unsolved mysteries are not failures of science, they're opportunities, invitations for future generations to explore and discover, to push the boundaries of knowledge even further than we have. Every answer raises new questions. Every discovery reveals new mysteries. That's not a bug in the scientific process. It's a feature. It means there will always be more to learn, more to explore, more to wonder about. The universe will never become boring or fully explained. There will always be frontiers, always be horizons, always be the next question waiting to be asked. As you lie there now, perhaps already half asleep, drifting in that pleasant space between waking consciousness and dreams, I hope you feel a sense of connection to the cosmos, a sense of belonging to something vast and ancient and beautiful. The universe is not cold and hostile and indifferent, despite how it might sometimes seem. It's your home, your origin, your context. You belong here. You arose naturally from the universe's evolution, from matter and energy, organizing themselves into ever more complex forms over billions of years. The atoms in your body were literally made in stars. The water in your cells was delivered by comets. The solid ground beneath you was assembled from countless collisions in the early solar system. You're woven into the cosmic tapestry at the deepest possible level. And tonight, as you sleep, the universe continues its slow expansion. Galaxies drifting apart, stars being born and dying, planets orbiting, black holes spinning, the cosmic microwave background cooling ever so slightly. The great cosmic machinery keeps running, following the laws of physics, creating complexity and structure and beauty. You're a part of that ongoing process, not just a passive observer but an active participant. Your consciousness, your ability to understand and appreciate and wonder, is one of the universe's most remarkable achievements. Closing thoughts. So rest now, dear learner. Let your mind drift peacefully. Let these cosmic thoughts blend with your dreams, creating strange and beautiful images as your unconscious mind processes what you've learned tonight. Perhaps you'll dream of stars being born in vast nebula, of galaxies spiraling through the void, of the Big Bang's first brilliant light spreading through empty space. Perhaps you'll dream of something entirely different, your mind weaving its own stories. Either way is perfectly fine. Sleep is your body and mind's way of processing the day's experiences, consolidating memories, making connections, restoring energy. Thank you for spending this time with me tonight, for joining me on this journey through space and time, from the beginning of everything to the present day. Thank you for your curiosity, for your willingness to learn, for lying there peacefully and letting these ideas wash over you like gentle waves. Thank you for being part of the Sleepy Professor community, for helping this channel grow and reach others who share your love of learning and your appreciation for the cosmos. If you enjoyed tonight's cosmic journey, Remember to like this video and share it with others who might appreciate this blend of education and relaxation. This gentle approach to learning about the universe's greatest mysteries. Subscribe if you haven't already, and turn on notifications so you won't miss future explorations. Perhaps next time we'll venture inside a black hole or explore the strange quantum realm where particles can be in two places at once, or journey to the edge of the observable universe to see the most distant galaxies ever detected. But for now, for tonight, this journey is complete. You've traveled 13.8 billion years in a single evening. From the very first moment of time to the present day, you've witnessed the birth of atoms, stars, and galaxies. You've learned about cosmic expansion, dark matter, and dark energy. You've connected your own existence to the vast cosmic story unfolding around you. That's quite an accomplishment, quite a journey. So close your eyes now, if they're not already closed. Feel the comfortable weight of your blanket, the softness of your pillow, the gentle rise and fall of your chest with each breath. Let your muscles relax completely, starting from your toes and working up through your legs, your torso, your arms, your shoulders, your neck, your face. Release any remaining tension. Let go of any thoughts or worries. Just be here now, in this moment, peaceful and relaxed and comfortable. The universe took 13.8 billion years to create this moment, this particular configuration of atoms and energy that is you, lying here, listening to these words, thinking these thoughts. You are impossibly unlikely, and yet, here you are, undeniably real, a conscious being capable of understanding your cosmic origins. That's something worth celebrating, worth appreciating, worth resting peacefully in gratitude for. The nature of time itself. Now, as your breathing becomes even slower, even more rhythmic, even more peaceful, let's contemplate something truly profound, something that lies at the very heart of the Big Bang theory. Let's think about time itself, that mysterious dimension through which we all move, always forward, never backward, 1 second at a time, relentlessly, inevitably. Before the Big Bang, there was no before. This sentence might sound paradoxical, even nonsensical, but it captures a deep truth about the nature of time. Time itself began with the Big Bang. It's not that the universe emerged at some moment within pre-existing time. Rather, time and space and matter and energy all came into existence together, simultaneously, as part of the same event. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question contains a hidden assumption that breaks down when examined carefully. There is no north beyond the northernmost point on Earth, and there was no before prior to the beginning of time. This concept challenges our everyday intuition so profoundly, so completely, because our entire experience is embedded in time. We remember the past, we experience the present, we anticipate the future. Our language is structured around temporal concepts before and after, then and now, yesterday and tomorrow. Our entire consciousness is organized temporally, with memories of the past informing our actions in the present as we plan for the future. The idea that time itself could have a beginning, that there could be a first moment with nothing preceding it, seems to violate something fundamental about how we understand reality. But Einstein's theory of general relativity, that beautiful mathematical description of gravity and space-time, teaches us that time is not absolute or universal. Time is flexible, malleable, relative. It flows at different rates depending on how fast you're moving and how strong the gravitational field is around you. If you travel very fast, close to the speed of light, time slows down for you relative to someone standing still. This isn't an illusion or a trick. This is a real physical effect confirmed by countless experiments. Astronauts on the International Space Station age slightly slower than people on Earth's surface because they're moving so fast in orbit. The difference is tiny, just a few milliseconds over their months in space, but it's measurable with precise atomic clocks. Similarly, time flows more slowly in strong gravitational fields. A clock on the surface of a massive planet ticks more slowly than an identical clock far from any massive object, out in the emptiness of intergalactic space. Near the event horizon of a black hole, where gravity becomes unimaginably strong, time slows down dramatically. From the perspective of a distant observer, an astronaut falling into a black hole would appear to slow down, moving slower and slower as they approach the event horizon, eventually seeming to freeze at the boundary, taking infinite time to cross it. But from the astronaut's own perspective, time flows normally, and they cross the event horizon in a finite amount of their own time, though they wouldn't survive the journey due to the intense tidal forces that would tear them apart. These strange effects show us that time is not the rigid, absolute framework Newton imagined, ticking away uniformly throughout the universe like some cosmic clock. Instead, time is woven together with space into a four-dimensional fabric called space-time. Events don't happen in space at particular times. Rather, events are points in space-time, with 3 spatial coordinates and 1 temporal coordinate, all equally fundamental, all interconnected. When we talk about the Big Bang happening 13.8 billion years ago, we're measuring time according to a specific reference frame, the reference frame of the universe itself, or more precisely, the reference frame of an observer moving with the average motion of matter in the universe, what cosmologists call the comoving frame. In this frame, the cosmic microwave background looks the same in all directions after accounting for small fluctuations and our own motion through space. This provides a natural cosmic time, a way to assign ages to different epochs of cosmic history. But here's something truly mind-bending to contemplate as you drift towards sleep. Different observers moving at different speeds through space would experience cosmic history differently, would measure different amounts of time elapsed since the Big Bang. A hypothetical observer, traveling at nearly the speed of light since shortly after the Big Bang, would have experienced far less time than 13.8 billion years, perhaps only a few million years from their perspective, depending on their exact speed. Time dilation would compress billions of years of cosmic history into a much shorter subjective duration. This relativity of time leads to fascinating philosophical questions. Is there a true cosmic time, an objectively correct answer to how old the universe is, or is time fundamentally relative, with different observers experiencing different durations, even for cosmic history itself? Most cosmologists adopt the comoving frame as a standard, a conventional choice that makes calculations easier and matches our intuitive sense of cosmic time. But it's important to remember, it's a choice, a convention, not an absolute truth imposed by nature. As you lie there, feeling so relaxed now, so comfortable, so peaceful, consider this. You are moving through time right now, every second that passes, traveling into the future at the rate of 1 second per second. But what is time, really? Is it something that flows like a river carrying us along? Or is it simply another dimension of space-time, with past, present, and future all equally real, and our consciousness moving through it like a spotlight illuminating different moments? Physicists and philosophers debate these questions endlessly, with no consensus reached. Time remains mysterious, even as we measure it with incredible precision. The Big Bang marks the beginning of time as we know it, the earliest moment our current physics can describe what happened at the absolute beginning. In the first 10 circumflex 43 seconds, that's
0.00000000000000000000000000 seconds.
Remains uncertain because quantum effects become important at such tiny scales. and we don't yet have a complete theory of quantum gravity that unifies quantum mechanics with general relativity. Perhaps time itself is quantized at the smallest scales, coming in discrete packets rather than flowing smoothly. Perhaps time emerged gradually from some more fundamental timeless quantum state, or perhaps time extends infinitely into the past in ways we haven't yet understood, with the Big Bang representing a transition rather than an absolute beginning. These are questions for future physicists to ponder, mysteries waiting to be solved by generations yet to come. For now, rest in the knowledge that you exist in time, moving forward through it one peaceful moment at a time, from the past through the present into the future, part of the great cosmic story that began 13.8 billion years ago and continues still. The possibility of other universes. Let your eyelids grow even heavier now, if they're not already closed, as we contemplate an even more speculative idea, one that pushes the boundaries of science into the realm of theoretical possibility. What if our universe, vast and ancient as it is not the only one? What if countless other universes exist beyond our cosmic horizon, forever unreachable, forever unobservable, but nonetheless real? This idea, called the multiverse hypothesis, comes in several different forms, each based on different physics and different assumptions. One version suggests that our observable universe, that 93 billion light-year bubble within which light has had time to reach us, is just one region within a much larger, perhaps infinite, space. Beyond our cosmic horizon, far beyond what we can ever see, space continues, filled with more galaxies, more stars, more planets. If space truly is infinite, and if matter is distributed similarly everywhere at sufficiently large scales, then somewhere out there, unimaginably far away, there might be exact copies of you, of Earth, of our entire observable universe. This sounds like science fiction, but it's a logical consequence of infinite space combined with finite possible configurations of matter. Another version of the multiverse comes from eternal inflation, an extension of the theory of cosmic inflation that we haven't discussed much tonight. Inflation proposes that in the very first fraction of a second after the Big Bang, the universe underwent an incredibly rapid expansion, growing exponentially, doubling in size every tiny fraction of a second for a brief period. This inflation explains several puzzling features of our universe, including why it's so uniform and flat. In the eternal inflation scenario, inflation never completely ends everywhere. While it ended in our region, giving rise to our Big Bang and our observable universe, it continues in other regions, constantly creating new bubble universes within an eternally inflating background. Each bubble would be like a separate universe with its own Big Bang, its own laws of physics potentially, forever isolated from other bubbles. Yet another version comes from quantum mechanics, that strange and counterintuitive theory describing the behavior of particles at the smallest scales. In one interpretation of quantum mechanics, called the many worlds interpretation, every time a quantum event has multiple possible outcomes, all outcomes actually occur, but in different branches of reality. The universe constantly splits into parallel versions, creating an ever-expanding tree of possibilities. In some branch, you made different choices today. In another branch, dinosaurs never went extinct. In yet another, Earth never formed. The number of parallel universes would be astronomical, growing exponentially with every quantum event. These multiverse ideas are highly speculative, controversial among physicists. Some argue they're not truly scientific, because we can never observe other universes, can never test predictions about them directly. If something is forever unobservable, beyond any possible measurement or detection, can we meaningfully call it part of physics? Or does it become metaphysics, philosophy, untestable speculation? Others argue that multiverse theories make predictions we can test indirectly, and that they arise naturally from well-established physics like inflation and quantum mechanics. The debate continues, passionate and unresolved. What's certain is that these ideas remind us how much remains unknown, how many mysteries still surround us. Even if we understand our universe fairly well, having traced its history from the Big Bang to the present, we can't yet answer whether it's the only universe, whether existence stops at our cosmic horizon, or extends infinitely beyond it in ways we're only beginning to imagine. As you drift closer to sleep now, your mind wandering, your thoughts becoming looser and dreamier, perhaps you can find comfort in this uncertainty. We don't have all the answers. We don't know everything. The universe, and perhaps the multiverse, retain their mysteries, their wonders, their ability to surprise us. That's beautiful. In its own way, it means there will always be more to discover, more to learn, more to wonder about. The adventure of science never ends. The quest for understanding continues eternally, each answer raising new questions, each discovery revealing new horizons. Life in the cosmos. Now, breathing slowly, peacefully, let's consider one more profound question before you drift fully into sleep. Are we alone in this vast cosmos with its billions of galaxies, each containing billions of stars, with planets orbiting many or most of those stars? Does life exist elsewhere? Are there other conscious beings out there, looking up at their own night sky, asking the same questions we ask, wondering if they're alone? We don't know the answer yet, though we're searching diligently. We've discovered thousands of planets orbiting other stars, called exoplanets, using various clever techniques. Some of these planets are rocky like Earth. Some orbit in their star's habitable zone, the Goldilocks region, where temperatures allow liquid water to exist on the surface. Not too hot, not too cold, but just right. Water is essential for life as we know it, the universal solvent in which the chemistry of life unfolds. But having the right conditions doesn't guarantee life will arise. We don't yet understand how life begins, how non-living chemistry transitions to living biology. It happened on Earth somehow, fairly quickly after our planet cooled enough to have liquid water oceans. But was this an easy transition, likely to happen on any suitable planet, or was it incredibly improbable, a lucky accident that might be unique to Earth in our entire galaxy? We simply don't know yet. This is one of science's greatest unanswered questions. If life is common, then intelligence might be too, and the galaxy could be full of civilizations. But we haven't detected any signals, haven't found any evidence of technological societies among the stars. This silence is puzzling, sometimes called the Fermi paradox after physicist Enrico Fermi, who asked, "Where is everybody?" Perhaps intelligent life is rare. Perhaps civilizations don't last long, destroying themselves or facing natural catastrophes before they can spread through space. Perhaps they're out there, but not sending signals we can detect. Or perhaps we're simply looking in the wrong ways. Or perhaps we are alone, or at least very rare, scattered so sparsely through space that we'll never encounter another civilization. This possibility is both sobering and profound. If Earth is the only place in the observable universe where life has developed consciousness, where matter has organized itself to contemplate its own existence, then we carry an enormous responsibility. We are the universe's way of knowing itself. We are consciousness arising from cosmic evolution. Preserving our civilization, our knowledge, our culture becomes not just important for us, but cosmically significant. Yet, even if we're alone as intelligent beings, the universe is far from empty or dead. It's filled with beauty, with spiral galaxies and glowing nebulae, with neutron stars and black holes, with planets and moons and asteroid belts. It's filled with complexity, with the intricate chemistry of interstellar clouds, with the nuclear physics of stellar cores, with the quantum mechanics of atoms. It's filled with history, with 13.8 billion years of cosmic evolution, from the Big Bang to the present. And if we're the only ones here to appreciate it all, to understand it, to find meaning in it, then perhaps that makes it even more precious, even more worth celebrating. The cosmic photograph. Every story, every family, every person has an old photograph tucked away somewhere safe, a snapshot of how things began, how they looked at the start, baby pictures, childhood memories, moments captured in time. For the universe itself, that photograph isn't tucked into an album gathering dust on a shelf. It's not hidden in a drawer or stored in a digital cloud somewhere. It's stretched gloriously across the entire sky, above and around you, visible from every point in space. It's called the Cosmic Microwave Background, or CMB for short, and it represents the oldest light we can possibly see. It's not starlight, shining from distant suns, burning hydrogen. It's not even the glow of galaxies billions of light years away, their collective starlight blended together. It's something far more ancient and precious. It's the faint afterglow of the universe itself, light that was released when everything was still incredibly young, unimaginably hot, and brilliantly bright beyond description. To truly understand what this light really is, what it represents and why it matters, picture the universe roughly 380,000 years after its beginning. Now, that might sound like a long time, and in human terms, it certainly is. Civilizations could rise and fall in that time. Empires could be built, but on cosmic scales, it's practically nothing, a blink, an instant. The merest fraction of the universe's current age. Back then, the universe was dense beyond imagination, fiery, and absolutely packed full of particles. Protons, electrons, photons of light, all jostling and colliding and bouncing off each other in what amounted to a thick glowing fog filling all of space uniformly. Photons of light couldn't travel freely through this fog because they kept constantly bumping into charged particles, particularly free electrons floating everywhere. They'd scatter, get absorbed, then be re-emitted in a new direction over and over again in an endless chaotic dance. A photon might travel a tiny fraction of an inch before hitting something, then scatter, then travel again, then scatter. The whole cosmos was, in essence, completely opaque, foggy. You couldn't see through it any more than you could see through a thick cloud. It wasn't that light didn't exist. Light was everywhere, filling every cubic centimeter of space, but it couldn't get very far, couldn't travel in straight lines for any appreciable distance before being bounced around again and again. Imagine trying to see through the thickest fog imaginable, so dense that light only travels a few centimeters before hitting a water droplet. That's what the early universe was like. Opaque, glowing, but opaque. Then, as the universe steadily expanded outward, as space itself grew larger, something crucial happened, a transformation. It cooled down, temperature dropped, and in that gradual cooling came a singular, pivotal moment of clarity, a cosmic dawn. When the temperature dropped to approximately 3,000 degrees Kelvin, which is still incredibly hot by our everyday standards but cool by cosmic ones, cooler than the surface of many stars, protons and electrons could finally join together, combining to form neutral hydrogen atoms. That simple act, electrons finding homes in orbit around atomic nuclei, suddenly changed absolutely everything about the universe's nature. It was like flipping a light switch. Without hordes of free electrons constantly scattering light in all directions, without that fog of charged particles, the universe went from completely opaque to transparent almost overnight. Well, overnight in cosmic terms anyway. It actually took a few thousand years for the transition to complete across all of space, but that's nothing, a cosmic eye blink. Photons could finally travel freely through space, unimpeded, for the very first time in cosmic history. They were liberated, set free, released from their constant bouncing and scattering, and they've been traveling in straight lines ever since for over 13 billion years, journeying across the expanding cosmos. Astronomers have a technical term for that pivotal moment. They call it the epoch of recombination, or the last scattering surface, because it represents the last time most photons scattered off electrons before beginning their free journey through space. It's like the universe suddenly became transparent, and light could finally see where it was going. Those very first free photons, released when the universe became transparent, are still traveling today, right now. They're still moving through space. They never stopped, but their energy has been stretched and softened by more than 13 billion years of continuous cosmic expansion. What was once a searing orange-white glare, bright enough to rival the surface of a star, has been stretched and stretched until it now hums gently in the microwave range, a form of electromagnetic radiation far beyond what human eyes can detect. It's too red for our eyes. The wavelength is too long. If your eyes could somehow tune into microwaves, if you possessed that superpower, if you could suddenly see that part of the spectrum, the entire sky would glow with an almost perfect uniformity, a pale, gentle wash of warmth coming from absolutely every direction at once. North, south, east, west, up, down, everywhere. It would surround you completely, uniformly, like being inside a glowing sphere. No matter which way you turned your head, you'd see the same faint glow. The CMB isn't just some abstract theoretical concept that exists only in equations and textbooks. It's real, physical, measurable radiation actually filling all of space right now. It's everywhere, between the stars, behind the distant galaxies, right here in your living room, passing through your body this very second. Countless microwave photons are streaming through you right now as you lie there. Ancient light from the beginning of time, and you can't feel them at all. If you ever used an old television set with analog reception, one that showed fuzzy static when not tuned to a channel, one of those old cathode ray tube TVs from before everything went digital, about 1% of that random static, those dancing specks of black and white noise on the screen, actually came from this ancient light. Those little dancing specks of noise on the screen were primordial photons that had been traveling since the dawn of time, journeying across billions of light years, bouncing off your TV antenna just before they reached the end of their impossible 13 billion year journey. They traveled all that way, across the entire observable universe, just to become static on your screen. There's something almost poetic about that, almost sad, but also beautiful. At first glance, when you measure it carefully with sensitive instruments, the cosmic microwave background looks astonishingly, almost impossibly smooth. No matter where in the sky you look, no matter which direction you point your detector, it has essentially the same temperature, about 2.725 degrees above absolute zero, to be precise. That's 2.725 Kelvin, or about minus 270 degrees Celsius. Incredibly cold, nearly as cold as physically possible. That kind of uniformity across the entire observable universe is actually one of the great wonders of nature. Across distances of billions upon billions of light years, separating regions that seem like they should have no connection to each other, the temperature barely varies at all. The differences are only a few millionths of a degree, 30 millionths to be exact, 1 part in 100,000. Yet hidden carefully within those tiny ripples, those infinitesimal variations in temperature, are the seeds of absolutely everything we see in the cosmos today. Those faint variations, the slightly warmer and cooler patches scattered across the sky in a seemingly random but actually very specific pattern, represent regions of just slightly higher or slightly lower density in the young universe, where things were just a little bit denser, just a tiny fraction more compressed. Gravity could begin its patient work. It could start to gather matter together over millions and billions of years. And over the course of those billions of years, those tiny initial fluctuations, those quantum ripples imprinted in the fabric of space during the first fraction of a second, grew and amplified, and eventually collapsed into the galaxies, galaxy clusters, and vast cosmic webs of structure we observe today. The universe today, with all its complexity, all its beautiful structures, traces back to those tiny temperature differences. It's genuinely humbling to think about. Every star you've ever seen, every planet ever discovered, every night sky ever enjoyed by anyone, anywhere, every astronomical photograph ever taken, all of it, absolutely all of it, traces back ultimately to small wrinkles in the texture of that ancient light, to patterns imprinted 380,000 years after the beginning, to quantum fluctuations that got frozen into space during cosmic inflation. Everything has a history, and the history of cosmic structure begins in that ancient glow. Detecting the CMB wasn't something scientists originally set out to do in a planned, deliberate way. The discovery was actually accidental, which makes it even more delightful. It's one of those wonderful stories where people looking for one thing found something far more profound. In the early 1960s, two engineers named Arno Penzias and Robert Wilson were testing a very sensitive radio antenna in New Jersey. It was a horn-shaped antenna originally built for satellite communications. They worked for Bell Labs, the famous research institution, and they were preparing the antenna for satellite communications work. Nothing cosmic, nothing profound, just mundane telecommunications. But no matter how carefully they cleaned and calibrated their instrument, no matter how many adjustments they made, checking everything repeatedly, they simply couldn't get rid of a persistent, annoying, faint background hiss in their data. It was always there, every measurement, every test, always the same mysterious noise. They thought initially it might be interference from New York City nearby, maybe radio signals from civilization, car ignitions, radio stations, electrical equipment. They checked everything they could think of. They looked for sources of noise. They tested their equipment again and again. They even discovered that pigeons had been nesting inside the antenna horn, leaving droppings everywhere that might affect the measurements. They addressed that particular problem with remarkable dedication, cleaning everything meticulously, removing every trace of what they politely called white dielectric material. Yet still, the mysterious hiss remained, unchanging and unexplained. Same temperature, same intensity, coming from every direction equally. Meanwhile, just 30 miles away at Princeton University, a group of theoretical physicists led by Robert Dicke had been preparing an experiment to look for exactly such a signal. They were searching for the predicted residual glow from the early universe, the afterglow that theoretical models said should exist if the Big Bang theory was correct. They'd been planning, building equipment, getting ready to search for something that might not even exist. When Penzias and Wilson finally learned about that work, when someone mentioned to them that Princeton was building a detector to search for primordial radiation, they suddenly realized with shock and wonder that their troublesome static wasn't interference at all. It wasn't noise to be eliminated. It wasn't pigeons. It wasn't New York. It was signal. It was the oldest light in existence, announcing itself through their antenna. They'd been trying to eliminate the very thing others were desperately trying to find. It was one of those wonderful, magical scientific moments where confusion and frustration suddenly transform into revelation and discovery. The engineers had quite literally stumbled upon the cosmic afterglow of creation itself, completely by accident. They were looking for something mundane and found something eternal. They discovered the echo of the Big Bang while trying to test a communications antenna. The discovery earned them the Nobel Prize in Physics in 1978, which seems fitting. Sometimes the universe reveals its secrets to those who are simply paying careful attention, even if they don't know what they're looking for. Over the next several decades, Astronomers worked to refine those first rough measurements, to map the CMB in ever greater detail, to understand its patterns and what they meant. Ground-based detectors were useful but limited, because Earth's atmosphere absorbs and distorts microwave radiation. Water vapor in the air is particularly problematic, so the search for precision inevitably moved to space, above the obscuring blanket of air that surrounds our planet. In 1989, NASA launched the Cosmic Background Explorer satellite, mercifully shortened to the acronym COBE. It was the first space mission specifically designed to map the CMB in detail across the entire sky, and it succeeded brilliantly, exceeding all expectations. COBE confirmed that the radiation followed an almost perfect black body spectrum, exactly precisely what theoretical predictions said it should look like for light that had been cooled by billions of years of cosmic expansion. The match was extraordinary. The theory had predicted a specific curve, and nature provided exactly that curve. The discovery and the precision of the measurements earned John Mather and George Smoot the Nobel Prize in Physics in 2006. It also cemented the Big Bang model firmly as the leading, most successful explanation for our universe's origin and evolution. Alternative theories, like the steady-state model, simply couldn't explain this radiation. Where would it come from in an eternal universe? The CMB was the smoking gun that proved the universe had a hot, dense beginning. But COBE, remarkable as it was for its time, was really just the beginning of our exploration. Its resolution was limited. It could see the overall glow but not fine details. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, called WMAP, and named after physicist David Wilkinson, to take an even closer, sharper look at the ancient light. WilkIMAP revealed those tiny ripples I mentioned, the minute temperature differences scattered across the sky, with absolutely stunning clarity and precision. What had seemed boringly uniform with earlier instruments, just a smooth glow, was suddenly revealed as a beautiful map of delicate texture and structure, a baby picture of the cosmos in exquisite, unprecedented detail. You could see patterns, structures, regions slightly warmer and cooler, arranged in specific ways. It was like going from a blurry photograph to a high-definition image. From that detailed map, scientists could infer all sorts of fundamental properties of the universe. The universe's precise age, its composition, what percentage is ordinary matter versus dark energy, its overall geometry, whether it's curved or flat, the amplitude of the initial quantum fluctuations, even predictions about the number and properties of neutrinos. Everything was encoded in those ripples. It was like reading the universe's birth certificate written in light, a cosmic Rosetta Stone that could be decoded with the right mathematical tools. A decade later, the European Space Agency sent up Planck, an even more sensitive satellite with finer resolution and better instruments. Planck's data refined our understanding still further, narrowing the age estimate of the universe to about 13.8 billion years, with remarkable precision. The uncertainty is now just tens of millions of years, which is astonishing given that we're measuring something billions of years old. It confirmed that the universe's geometry is remarkably, almost perfectly flat, not curved in any detectable way. If the universe were a curved surface like a sphere, we'd see distortions in the CMB pattern. We don't. It's flat to within measurement precision. It also measured with extraordinary accuracy how much of the cosmos is made up of ordinary matter like atoms, about 5%, versus dark matter that we can't see directly, about 27%, versus dark energy driving accelerated expansion, about 68%. All of that knowledge, everything we now know about the universe's overall structure and ultimate fate, emerged from careful analysis of the faint pattern of light released when the cosmos was less than 500,000 years old. It's extraordinary when you think about it. We can reconstruct the universe's composition by studying ancient light, by measuring tiny temperature differences across the sky, by applying mathematics and physics. It's one of humanity's greatest intellectual achievements. When you see those colourful maps of the CMB, often painted in exaggerated blues and reds for visual effect, remember something important. Those colours are dramatic exaggerations created for clarity, to make the tiny variations visible to the human eye. The real temperature variations are only a few 10,000ths of a degree, tiny, almost nothing. If you could actually see the CMB with your eyes, it would look perfectly uniform. You wouldn't see any structure at all without instruments. Yet those slight, subtle imperfections represent everything. Absolutely everything. Without them, without those initial quantum fluctuations that got stretched by inflation and imprinted in the CMB, the universe would have remained a boring, uniform mist forever. There would be no stars condensing from gas clouds, no galaxies spinning in the darkness, no planets, no chemistry, no life, no one around to look back across time and wonder how it all began. The ripples in that microwave background are quite literally the blueprint of all cosmic structure. They're the seeds from which complexity grew. Remove them, and the universe would be empty and boring. Include them, and you get the rich tapestry of structure we observe. It's remarkable how much depends on such tiny initial variations. The cosmic microwave background is not only a historical relic from long ago, it's also an incredibly precise measuring tool, perhaps the most precise tool we have for cosmology. By studying its pattern of ripples in fine detail, scientists can measure fundamental properties of the universe: its size, its rate of expansion, its composition, the nature of dark matter and dark energy, even its long-term fate, billions of years hence, whether it will expand forever or eventually collapse. The peaks and valleys in the CMB's temperature map, when you analyze them mathematically through something called the power spectrum, actually correspond to acoustic waves, to sound waves, if you will, pressure oscillations that rippled through the hot plasma before light was freed. Imagine the entire universe ringing like a bell, with different notes corresponding to different size scales. Those sound waves, frozen into the fabric of the universe like ripples frozen into ice, act as a cosmic yardstick that helps astronomers measure vast distances across billions of light years with remarkable accuracy. It's as though the universe deliberately left behind a faint soundtrack of its own beginnings, a recording of its first moments, one we can still detect and analyze today simply by carefully studying the pattern of the sky, the music of creation, still playing softly if you know how to listen. What makes the CMB so profoundly beautiful, so conceptually elegant, is its strange dual nature. It's both incredibly ancient and eternally present, both then and now, both a record of the past and something happening in the present. Every direction you look when you study it, you're gazing at exactly the same moment in time, frozen forever. The moment when the cosmos first became transparent, 13.8 billion years ago, the moment visibility began. In that very real sense, the CMB is the nearest thing we have to a photograph of the birth of light itself, the moment visibility began. The cosmic dawn. Before this, the universe was opaque. After this, it was transparent. This was the transition. This was the transition, and we can still see it, still study it, still learn from it. When you stand outside on a dark, quiet night like tonight, every photon of light that gently touches your skin carries a unique story about where it came from and how long it traveled. Starlight from nearby stars might be just a few years old, relatively fresh. Light from distant galaxies could be billions of years old, ancient by any measure. But the oldest photons of all, still humming faintly in the microwave frequencies all around you right now, those tell the very first story. the original story, the story of the beginning, that whispering, all-pervading glow is quite literally the universe's memory of itself. It fills every corner of space with the soft, faded aftertaste of its fiery youth. It's everywhere, always, a constant reminder of where we came from. 13.8 billion years ago, those ancient photons began their long journey across space. And tonight, right now, as you lie there listening to these words, they are still faithfully arriving one by one, patient and persistent, the oldest travelers in all of existence. They've seen everything. They've witnessed the birth of every star, every galaxy. They were there when the first stars ignited, when the first planets formed, when life began on Earth, and now they're here with us, sharing their story if only we listen carefully enough with our instruments and our mathematics. Rest now. Let the image of that ancient light surround you. You're bathed in the afterglow of creation, always.